Now section 5.2 we're looking at inclined planes, and this is really an absolute classic of mechanics and physics textbooks for decades and probably hundreds of years. These diagrams are really a bread and butter sort of bit of maths. This is the one that you'll be having flashbacks of in years to come, because you'll have seen so many diagrams that work like this. So it's really important that our first sort of introduction to them, we get a few of the basics right, and then if we slowly build up the difficulty, hopefully you won't get too many horrible flashbacks of these sort of diagrams. The advantage with mechanics, I always think, though, is once you get the idea, it tends to stick in your head. So if this is tricky at first, don't panic, stick with it. I've had a lot of students found these ideas really hard. That's absolutely not unusual. But if you keep going, you'll get there in the end. And when you do, you'll look back and think, oh, right, well, I get it now. I don't quite understand why it was so difficult in the first place. It's just one of those things that seems to be how it hits people. It is difficult to get your head around. But when it sinks in, it starts to seem almost obvious. So this is the situation we've got. We've got an object, and I'm taking this 15-degree angle from example 5. I may as well start with the same angle that they're starting with. But basically, I've got an object sitting on a slope, okay? And this is what we call an inclined plane, right? So imagine we've got a, here is a piece of paper, that's a plane. If I incline it, so if I do that to it, then it's inclined, there's an angle, right? So I've got a slope like this, and I've got an object sitting on there. Now, what's happening to that object? Well, first of all, its weight is pushing downwards. But its weight doesn't go along the slope, and it doesn't go this way, perpendicular to the slope, it goes vertically downwards. There is something that's stopping it accelerating there, right? If that was it, if that was the only force going on, this box would have to be accelerating downwards, and we know that doesn't happen. We know that if we put something on a slope like this, it doesn't suddenly accelerate down through it. And why is that? Well, it's because the slope is providing a resistance force. But the resistance force, the reaction force, happens at 90 degrees to the slope. Okay, so that's a right angle there. Now, here is a really useful thing, and I'll draw a separate diagram of this. If you've got a slope like this, and if I draw a line at 90 degrees to the slope, and if I draw a line vertically downwards, this is what we're always going to have, right? This is always going to be the line of normal reaction force, which is going to be 90 degrees to the slope, and this is going to be the weight of the object sitting on the slope, like we have here. So here we've got this, and here we've got this one. Now, let's think about these angles. That's 90 degrees, because that's vertical there, that's horizontal there. Here's an angle. That's 90 degrees, again, vertical and horizontal. This here, let me get my red pen. This here, can you see that is 90 degrees because this is perpendicular to the line of this slope. So if that's 90 degrees, well, this one here, these three angles are in a right angle triangle, so this is 90 minus theta. Therefore, this angle here must be theta. Okay? Now that is the fact that this angle here and this angle here are the same. Again, I think we mentioned that in the moments chapter briefly. That is something that we get to use all the time, and it's a very, very helpful fact. So the thing you do straight away is you put that angle in as 15 degrees. So you keep going along the line of the resistance force, that is 90 degrees to the slope, and you put in 15 degrees there. Now the reason we put 15 degrees there is because with all of these things, what we're going to do is, instead of thinking vertically and horizontally, we're going to think parallel to the line of the slope and perpendicular to the line of the slope. Now you need to say that, so we're going to say we will resolve forces perpendicular to the line of the slope. There's no acceleration going on, it's not lifting off, it's not accelerating down through here. So we're resolving forces, we're not applying F equals ma. But we're not going vertically, we're going in this direction now. Now, another notation where we'd say resolve perpendicular, just write perpendicular. I've seen people do this sort of thing for resolve perpendicularly to the slope, or perpendicularly with an R for perpendicular, R with the end of the word. Whatever we're doing, we need to say we're going perpendicular to the slope. This is a fairly standard notation, but make sure you don't mix it up with that. Don't say we're going vertically and then do the resolving perpendicular to the slope. So we're going to resolve perpendicular to the slope. What have we got? We've got R. Now in this particular example, this is a 10 Newton force. This one is just a reaction force. We don't know how big it is. So, pushing out from the slope, we've got r. Pushing down into the slope, we've got 10 newtons cos 15. Can you see that? That's the speed that you need to be able to do these things at. Here's my right angle triangle. 10 newtons is the hypotenuse. 15 degrees is the angle here. We're adjacent to that. So r equals 10 cos 15 degrees. Resolving, oh, sorry, not resolving. Here, this thing, because it says here we have a smooth slope, in real life, if this was sitting on the slope and it wasn't moving, the thing that would be keeping it there would be friction. And the friction would be stopping it moving, and therefore there would be an extra force on this diagram acting in that direction. Now, we haven't got as far as the friction bit yet, so this is a smooth slope. If this is a perfectly smooth slope and it's not horizontal, then this thing would have to be sliding down it. And we see that on the diagram because if you look at the forces, we've got this one pushing out and this one pushing down, but in the line of down the slope, the only thing happening is that this 10 Newton force is going this way a little bit. There's a component of this 10 Newton force acting this way. So it must be accelerating. F equals ma. In this direction, parallel to the slope, we go F equals ma. By the way, I don't have to worry about this thing being actually parallel to the line on my diagram. I know what I mean here. It means going parallel to the slope. And that's a reasonable notation even for an exam, even for an A-level exam on this syllabus, I should say. So 10 newtons, don't need newtons in my equation, so 10 times sine 15 degrees, that's that component of that force there, equals mass, which is 10 in this question, 10 kilograms, times acceleration, okay? So if we now look at what the question's actually asking us on example 5, draw a force diagram, well, we did that one, calculate the magnitude of the normal reaction, so calculate r, well, that comes from this equation here, and then calculate the acceleration, well, that came from this equation here. Now, usually the equations won't be quite so straightforward and there'll be more complicated diagrams, but that is the essence of everything that we're going to do here. So I'm just going to take example 6, we'll read through it, and in fact I might even do example 7 as well, even though they're the same, because this is such an important idea. We have a particle of mass m is pushed up a smooth slope by a force of magnitude 5g. So there's my, oh, they've got a circle, I'll put a circle. So there's my P. This 5g force is acting at 60 degrees to the slope. Now, they've put that on, if you can see, as a sort of, as though it's a pushing force, pushing from this direction, which of course is what would have to happen. But I'm going to put it on like this. I'm going to put it on acting that way, because I like to start my forces at the object and move them away, as though they're all sort of strings attached to the object pulling. Now, physically, of course, we couldn't do this. You know, imagine this is a hill. This would then be something inside the hill, sort of pulling it. You know, so there's something underneath the slope, and of course, you'd have to go through the slope there. But I know what I mean by this. I mean, there's a force going in that direction. Obviously, the way to apply that force will be as a pushing force from here, but it's I feel like it makes things easier to deal with it that way. It says that it's 60 degrees to the slope. Well, in that case, this angle here is 60 degrees. And if you'd like to see that, look, there's 60 degrees there, and these two are opposite angles. Okay, what else do we have? We have that the slope is at 30 degrees to the horizontal, that this magnitude here is 5g newtons, and the particle accelerates at the slope. So the acceleration equals 0.5 meters per second, and show that the mass of the particle is, so the mass of the particle is what we're after. So this thing has a weight, is acting down mg. There is a force there, the resistance force, the reaction force from the plane, which at the moment we don't know anything about it, so we just call that one r. mg acting downwards, r acting inwards. Those are the two forces that we put in every single time. And then I'm going to put a dotted line in here and in here to represent the two components of this mg force here. And I'm going to go straight for that angle there, is that angle there, so that's 30 degrees, and there's a 90-degree angle there. So what do we have now? Well, we have, this is not accelerating in this direction. So in this direction, we're going to resolve forces. Forces out from the plane equals forces into the plane. Forces out from the plane is r. There's only that r. What are the forces into the plane? Can you see we've now got 3 forces in the diagram? It gets a bit more complicated because we've got to do a bit more work because there are 3 forces. In harder questions there'll be more than 3 forces, but we still do the same thing. mg cos 30, can you see that? That's this line here. mg is the hypotenuse of this right angle triangle, 30 is that angle there, and this is the adjacent. So r equals mg cos 30 degrees. Then what about this force here? Well, this force here, I'll put this on in red just to make it a little bit different so we can see it a bit more clearly perhaps. We can split it up into that component and this component. So this force here is pushing up the plane and down into the plane. What bit of it's pushing down into the plane? Well, it's 5g opposite the angle, so 5g sine 60 degrees. Then, have you noticed, look, I'm writing the equation down and then I'm moving on. I'm going to go in this direction now. In this direction, they've told us that it's accelerating up the plane. Now, from the diagram, I wouldn't know if it's accelerating or not. Perhaps this force and this force balance each other out. There is a force up the plane, there is a force down the plane. Maybe they balance, maybe they don't. But the question tells us that it's accelerating. So F equals ma. It also tells us it's accelerating up the plane. So forces up the plane, take away forces down the plane is going to be my resultant force. So 5g cos 60 is this force here. Down the plane, I've got mg sine 30. And I know that I do up the plane, take away down the plane, because it tells us that it's accelerating up the plane. And that is equal to m mass times the acceleration. So there is equation number 1, and here is equation number 2. And now I'd stop and look at this and think, okay, well, what is it that they wanted me to find? And they wanted me to find the mass. Now, in this particular question, can you see that I didn't need this one? This equation here has got m in it, and there's nothing else other than m in it. Everything else that's there, I know what it is. So I could have just applied F equals ma in this direction. And if you look in the example, that's what they're telling you to do. We just say we'll go in that direction. Now the problem with that is, how was I to know that this was enough? In all of these questions, there are 2 things you can do. You can think in this direction, you can think in this direction. And it's not always obvious from the question which of those things you're going to need. In almost all the questions, by the time you hit an A-level exam, you're going to need the equation for this direction and you're going to need the equation for this direction. So my advice to you is just get into the habit of writing both of those equations down and then looking at it and thinking, well, now what do I need? Now, perhaps you'll be lucky. Perhaps you'll see a question and you'll think, well, in this case, I only need one of these equations. But most of the time, you'll need both of them. So write them both down. Don't simplify them straight away. Just get them written down and then work from there afterwards. Now we've got these both written down. Look at them, think about solving them. If I needed R, that's the other question they couldn't have asked us, what's the resultant force? Well, I would have needed to solve equation 2 to get the value of m, and then substitute that into equation 1 to get the value of r. So maybe I would have needed both of these. And on most exam papers, they would have asked you for m and r. Most exam papers, on the question that look like this, there will be some things missing, and those things that are missing are all the things you've got to find. Sometimes it's 1 thing, sometimes 2 things, sometimes it's 3 things. If there are 2 things missing, these 2 equations will get you the answer. If there are 3 things missing, then there must be some other information going on as well in the question to make a 3rd equation, okay? So I suppose let's just finish it off. 5g, well, cos 60 is a half, sine 30 is a half, m over 2. So if I times everything by 2, let's just see, are we heading in the right direction? Here we are. 5g, I put all the m's on one side, m plus mg, so that's 5g equals m, brackets 1 plus g. So m equals 5g over 1 plus g, which is what they were looking for, and kilograms is our unit because we're working in, we're looking for a mass, okay? So there's example 6. We have quite a long video, but this is quite an important idea. If you are happy there, then that obviously makes total sense. Move on, have a go at the exercise yourself. I'll look at example 7 for anybody interested. So here we have a particle of mass 2 kilograms, and again, it's on an inclined plane. So here's my inclined plane, here's my particle, mass 2 kilograms, so 2g newtons pushing downwards. There's going to be a reaction force like that. Those two forces we put on all the time. We've got a 4 Newton force, it says here, that acts parallel to the slope. Now, it doesn't say that it's in equilibrium. It doesn't say it's accelerating so far when I'm reading the question. I'm putting my 4 Newton force on in this direction. In the textbook, they put it on like this. They put it on as a pushing force. I put it on as a pulling force. We don't know whether it's a pulling force or a pushing force in reality. I just like to have my forces starting at the object and moving away from them. The slope is inclined at an angle alpha to the horizontal, where tan alpha equals 3/4. Work out the acceleration of the particle. So it does say it's accelerating, okay? Now, it could be accelerating up the plane. This thing could be pushing it up the plane. And it could be accelerating down the plane. We don't actually know yet, because maybe this force is trying to stop it, but it's moving down the plane, okay? Imagine that force wasn't there, this would be sliding down the plane. If that force is there, maybe it's still sliding down the plane despite this force trying to stop it. So how are we going to deal with this? Well, we're going to go like this and like this, so we can picture our vertical, well, not our vertical, our parallel and perpendicular components of this force. And then we're going to think perpendicular to the plane. We will resolve, and we get R pushing outwards. Here's alpha here. So R equals 2g adjacent to the angle cos alpha. R equals 2g cos alpha, and that's it. In that direction, we've got F equals ma. Oh, F equals ma, not F equals mg. Oh dear. Now, let's assume that we're accelerating up this plane. So we'll make this the positive direction. We'll make that, as far as we know, the direction of acceleration. Now, we might be wrong, and if we're wrong, then our acceleration will come out negative. It won't be a problem. So 4 pushing in the direction we think we're accelerating, and going this way, 2g sine alpha. And hopefully that's now becoming familiar, opposite the angle. Hypotenuse is 2g, opposite the angle, so sine. Is mass, and the mass in this case, it tells us, is 2 kilograms times a, which is the acceleration. And now I've got equation number 1 and equation number 2, and the thing it was asking for was alpha, okay? Well, if we look at these two equations, are we going to be able to find it? Hopefully we are. Sorry, no, it's not looking for alpha, is it? It's looking for a. We know, when we look at these equations, we've got an r, an alpha, and an a that are missing. And we think, we've got 2 equations, we've got 3 unknowns, so we're in trouble, except that sitting here is our salvation. We know what alpha is, right? We can work out alpha from that. So if we work out alpha and put those in here, then we can work out r and a from 2 simultaneous equations. Well, they're not even simultaneous equations. One equation to tell us r, one equation to tell us a. Okay? Often they'll be simultaneous. In this case, they won't. They're not. Now, I could, of course, work out alpha as tan inverse of 3/4, and then I can find sine and cos. But in this case, it's often more helpful to do it like this. Look. Imagine an angle alpha. The tan is the opposite over the adjacent. So that side and that side are in the ratio 3:4. And then if we use Pythagoras' theorem, this must be a 3-4-5 triangle. So in that case, sine of alpha is 3/5, and cos of alpha is 4/5. So this is r equals 2g cos of alpha, so times 4/5. And 4 minus 2g sine of alpha is 3/5 equals 2a. Now, have you noticed, by the way, I'm going to change that to line 1 and that to line 2. You notice I'm really ignoring what the question's asking us. The question is asking us to work out the acceleration of the particle. So now I know that I only need this equation, but I'm still sort of automatically going back and fiddling with this equation, because on so many of these questions, you need both equations. And even if in part A you only need this one, then in part B you need this one. So it's just a really good habit to get into, to deal with this direction, deal with this direction, write down both the equations, get them into a nice usable form, and then work from there, okay? Now in this case, to do this, we just have to finish off solving this equation, and they do that for you in the textbook. on page 98. So that's it. Good luck with example 5b. Put a lot of practice and careful work into that, because we use the ideas from 5b an awful lot. Good luck.